Hello, today we're continuing in our A-level physics revision series looking at the nuclear radius. There is almost certainly more information in this video than you'll need in your A-level syllabus, but I hope it will give you useful background information. The year is 1900 and the atom is no longer being regarded as an indivisible billiard ball. Thanks to the work of J.J. Thomson, it is now regarded that the atom is consisting of two bits. The bulk of it is positively charged, but within that positive charge there are bits of negative charge. And that gave rise to the idea of what's called the plum pudding model or the current bun model, where the bulk of the atom is regarded as the pudding, the positive dough, and the dots in the atom are regarded as the negatively charged plums or raisins or currants or what you will. But then Rutherford performed his famous experiment, which I've covered in an earlier video and which we'll come to later in this one, which established that the current bun or plum pudding model was not correct and that instead the atom consisted of a central nucleus which was very small and which was positively charged, and that there were what you might call orbiting electrons, which were the negatively charged bit, and that everything else in the atom was simply empty space. All the mass of the atom was contained in the very small central nucleus. And if you wanted some idea of the scale, then if the entire atom were the size of an ordinary room, the nucleus would be the size of a grain of sand. We now know that this central nucleus is in fact made up of protons and neutrons all held together within the nucleus. Protons are positively charged, neutrons have no charge, and that begs the question that if protons are positively charged, they ought to repel one another, because like charges repel, and if they repel each other there shouldn't be a nucleus, because it shouldn't be possible to have two or more protons in a nucleus. But since nucleuses or nuclei are stable, that must be because there is something that is holding them together, and whatever is holding them together is stronger than what's trying to push them apart, and the thing that's holding them together is the strong nuclear force. So we say that the strong nuclear force must be stronger, that's why it's called strong, than the electromagnetic force or the Coulomb force, which is trying to push them apart. And the question for this video is, what is the size of that nucleus? And more accurately, we want to know what is the size of the radius of that nucleus. Well, let's come back to the famous Rutherford experiment, which was performed in the very early 1900s. Rutherford took an alpha source, that is, it was radium-226, and the alphas were targeted at a target which was a very, very thin piece of gold foil. And then on the other side he had a detector, and that detector was on a swivel, so that he could actually move the detector right the way round in almost a full circle to detect whether alpha particles came off here, 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 or wherever. The energy of the alpha particles was 4.87 MeV, and these here are alpha particles hitting the gold foil. Now what he found was that the overwhelming majority, virtually all of them, just go straight through. And the reason they just go straight through, of course, is that when they hit the atom, for the bulk of the time, there's nothing to hit, because most of the atom is empty. And consequently, the alpha particles just go through the gold atoms because there's nothing to stop them. But every so often, the alpha particles, which consist of two protons and two neutrons, so it's two positively charged particles, would come close to the gold nucleus, and a gold nucleus consists of 79 positively charged protons. And when that happens, you would get the Coulomb law of repulsion, and that would cause the alpha particles to deflect And so consequently you would find that alpha particles would be coming off, but not many. Indeed, what Rutherford found was that some of the alpha particles sort of seemed to bounce back. So strong was the Coulomb force of repulsion. Now what Rutherford considered was this situation here. Let's say that this is the gold nucleus with 79 protons. He considered the alpha particle that was heading straight for that gold nucleus. Remember, most alpha particles will go way to the side of the nucleus and hardly be influenced at all. They'll just go straight through an empty atom and out the other side. But what about the alpha particle that is on a collision course for the nucleus? Well, you've got an alpha particle which consists of 2 positively charged protons coming towards a nucleus which consists of 79 positively charged protons. There is therefore going to be a force between the two, and that force is equal to a constant times the charge on one particle, that's the alpha particle, times the charge on the other particle, that's the gold nucleus, divided by r squared, where r is the distance between the two. So as you get closer, as the distance between them decreases, the force between them will increase. And it's a force of repulsion. So essentially, as this alpha particle comes towards the nucleus, it will be slowed down by the force of repulsion. And it will be slowed down, says Rutherford, right to the point where at some point it will stop. The force will be so great that it will stop, and then it will turn round and just come back on itself. So the alpha particle that's heading for the nucleus, says Rutherford, will slow down because there's a force of repulsion pushing it the other way until eventually it stops and then it goes back. What happens when that occurs? Well, says Rutherford, at this point here it has kinetic energy, and we know what the kinetic energy was, it's 4.87 MeV. And when it gets to this point here where it's stopped, it has 0 kinetic energy. But of course energy must be conserved, and so at this point all the energy must have been converted into potential energy. And the potential energy, or the electric potential energy, is given as Q1 Q2 divided by 4 pi epsilon 0 r, where 1 over 4 pi epsilon 0 is the same as K that I used here. And if you then simply switch these two around, so what you're effectively saying is that the kinetic energy has become the potential energy. So if potential energy equals this term, the kinetic energy must be equal to this term, because all the kinetic energy has changed to potential energy. And that means that what you can say is that if you just simply swap R and kinetic energy around, you get that the radius is equal to Q1 Q2 divided by 4 pi epsilon 0 times the kinetic energy. And we know that, just to give you the value, 1 over 4 pi epsilon 0 is equal to 8.99 times 10 to the 9. There will be units, but let's not worry about those at the moment. So Rutherford's idea, let's just review it again, is that the alpha particle slows down under the force of repulsion between the alpha particle and the gold nucleus until it stops, and then of course it goes back. At the point at which it stops, all the kinetic energy has been changed into potential energy. So kinetic energy becomes potential energy. The value of potential energy is given by this formula, and therefore kinetic energy equals this formula. And if you simply swap over the two terms K and R, you get a term for R, which is of course not necessarily the radius of the nucleus. It's simply the distance of closest approach. So I've rewritten the formula which we just derived for the radius, and now let's see if we can work out what that actually is. Well, Q1 is the charge on the alpha particle. The alpha particle has 2 protons, so that's 2 times the charge on a proton, which is 1.6 times 10 to the minus 19 coulombs, times Q2, which is the charge on the gold nucleus, and that's got 79 protons, so it's 79 times the charge on a proton, 1.6 times 10 to the minus 19, times, and now we've got the 1 over 4 pi epsilon naught term, which is 8.99 times 10 to the 9. That's all in the numerator, divided by the kinetic energy. Well, the kinetic energy, you remember, was 4.87 MeV. Well, to convert that to EV, you have to multiply by 10 to the 6. And to convert that into joules, you need to multiply by 1.6 times 10 to the minus 19. And you'll notice now that one of the 1.6 times 10 to the minus 19 terms cancels out. Now, observe that in this rather complicated equation, there are in fact only 3 terms that are true variables. That is the number of protons, number of protons in the alpha particle, number of protons in the gold nucleus, and the kinetic energy in MeV of the incoming alpha particle. All the rest, in a sense, are constants. So what I think, since we're going to do this calculation several times, it's not a bad idea to save us doing that complex calculation on a calculator every time. Let's just work out what R is in terms of 2 times 79 divided by 4.87 times a constant, where the constant is everything else apart from those 3 terms. And if you work out what that constant is, that is to say, what is 1.6 times 10 to the minus 19 times 8.99 times 10 to the 9 divided by 10 to the 6, you will find that that equals 1.44 times 10 to the minus 15. And the units, should you want them, are of course MeV meters. So now we can do the full calculation. We simply say 2 times 79 divided by 4.87 times 1.44 times 10 to the minus 15. And that comes to 46 times 10 to the minus 15 meters. Or, if you prefer, 4.6 times 10 to the minus 14 meters. Now, as I've said, that is not the radius of the nucleus. That is simply the distance of the closest approach of that alpha particle heading for the nucleus, where all the kinetic energy is converted to potential energy. It comes to a stop and then it goes back again. When it comes to a stop, according to this formula, the alpha particle is 4.6 times 10 to the minus 14 meters away from the center of the nucleus. Well, that's not necessarily the radius, but it gives us a flavour of how small the nucleus is. 10 to the minus 14 metres, according to this, which is 1/100 million millionth of a metre. Okay, so what's the next step? Well, this was Rutherford's continuing argument. Let us take the atom of the gold nucleus. So this is just one atom, and here's the nucleus with the 79 protons in the middle. And let's now consider different alpha particles. We remember always that the Coulomb force of repulsion, because it will be between an alpha particle and a gold nucleus, both of which have positive charges, the force of repulsion is Q1 Q2 over 4 pi epsilon naught r squared. And the key point here is that as r decreases, in other words, as an alpha particle gets closer to the nucleus, the force of repulsion will increase. So as r decreases, the force increases. So let's have a look and see what that means. First, we'll take the alpha particle we've already looked at. That's the one that's headed straight for the nucleus. And as we said, it gets to a certain shortest distance, it stops, and then it obviously goes back on itself and comes back to where it started. But now let's consider an alpha particle that comes in here. Well, it too will suffer, a force of repulsion, but it's a bit further away, so consequently the force will be slightly smaller. Furthermore, the force which is acting in this direction, will have a tangent or a coordinate point in the, as it were, north direction. So when that particle is influenced by the force, it will go back on itself like that, going through a very large angle. This is the angle that it's scattered through. Now let's think about the alpha particle that comes here. Well, that too is going to suffer a force, but not as great as the previous two, so its angle of scattering will be a little smaller, about 90 degrees. Now let's think about this alpha particle. This is even further away, the force is therefore even smaller, and so its scattering angle will be about 45 degrees. And then here's the next alpha particle. Well, that's a long way away, and so its force acting on that is going to be very, very much smaller. You'll get barely any change in angle at all. So what you can see is that the further away the alpha particle is from the nucleus coming in, the further away it is, the smaller will be the scattering angle. And just to indicate what I mean by scattering angle, if the alpha particle is coming in like this and it goes out like that, then the angle that it's scattered through is that angle there. So consequently, if the alpha particle comes in like this and scatters there, then the angle it's scattered through is a very large angle, theta there. So we're measuring that angle. It will be a small angle if the alpha particle is a long way away from the nucleus, and it will be a large angle if the alpha particle is very close to the nucleus. And we have a parameter which determines how close the alpha particle is. It's called the impact parameter. And the way we define that is if that's the nucleus and that's the line of, as it were, closest approach, that's the alpha particle that would hit the nucleus, were it not for the fact that it gets stopped and repelled, then if you've got an alpha particle that's coming in here and being diverted through some angle, then the impact parameter is the perpendicular distance between the line of closest approach and the line which the alpha particle is actually taking. And what you will see, we call that impact parameter is b. As b increases, in other words, as the distance from this line of closest approach increases, the angle of scattering will decrease. The further you get away, the smaller the angle will be. Okay, now I want you to imagine that you are the alpha particle headed for a gold nucleus. All right, or rather you're headed for a gold atom, let's put it that way. If you want to scatter through a very large angle, remember you've got to arrive very close to the nucleus. In other words, you've got to try and aim for the bullseye. You've got to be somewhere in this shaded region here if you want to scatter through a large angle. If on the other hand you're content to scatter only through a small angle, you've got a much larger target to aim for. To scatter through a small angle, you have to be much further away from the nucleus, so you've got to be somewhere in the shaded region here. Now I think you'll see that the area of the shaded region in the outer circle is much larger than the area of the shaded region in the inner circle. And if we assume that the alpha particles are arriving equally distributed, headed towards that target, far more alpha particles are going to arrive hitting this particular area, because it's a bigger area, than hitting this area in the middle here. And that gives rise to the concept of what is called a cross-section. In other words, if you're the incoming alpha particle, what is the area you have to hit if you want to scatter through a large angle? And obviously, the area that you're hitting is the area of a circle. That's just given by pi r squared. And so what we can say is that the cross-section, which is given the label sigma, for a particular angle will be equal to the area that you are to hit multiplied by some function of that angle. So the idea is that the greater r is, the smaller the angle will be through which you are deflected. So this cross-section both gives you an indicator of the number of particles that are likely to be deflected through that particular angle, or you can look at it another way, it gives a kind of indication of the probability of an alpha particle being deflected through that angle. The closer to the nucleus you come, the greater will be the angle of deflection, but fewer alpha particles will hit that area than will hit this area. Now we've already got a formula for r, so let's substitute that in. That gives us that the cross-section for any given angle of scattering is equal to pi times r squared. Well, that was q1, q2 divided by 4 pi epsilon naught times the kinetic energy squared times the function of theta, or theta. And it turns out that f theta is 1 plus cosine theta divided by 1 minus cosine theta. Now, two gentlemen by the name of Geiger and Marsden. Geiger is the one who gives his name to the Geiger counter, the radioactive monitor. Geiger and Marsden were Rutherford's assistants, and they did the actual experiment which bears their name, for which they get the credit, alpha scattering. What they did was they took that detector, here is the alpha source, hitting a gold target, and what they did is they had a detector that they could rotate right the way around, in fact almost through 360 degrees. And what they would do is they would measure the number of alpha particles given off for any given angle theta. And what they found was they got a graph that looks like this. This is the number of alpha particles at a particular angle, and that of course is going to be, as it were, proportional to the cross section. And this is the angle theta increasing in this direction. So this is 0 degrees and this is about 140 degrees. And this is what's called a log scale. A log scale is one where instead of going 1, 2, 3, 4, 5, 6, 7, you actually go up by tenfold in every step. So if this is 10, this will be 100, this will be 1,000, this will be 10,000, 100,000, and so on. So in other words, this condenses the scale, otherwise you need a piece of paper that's a mile long. And what they found was that the number of alpha particles according to the angle fell like this. And you might say that's plausible, that's a kind of a 1 over r squared term. The further out you go, the bigger r is, then the force falls off as 1 over r squared according to the Coulomb law, and that looks entirely plausible. As the angle increases, the number of alpha particles you detect rapidly decreases. So in other words, we can summarize that by saying that n is proportional to theta. As n decreases, the angle theta increases. Now we said that n, the total number that you detect of alpha particles scattered through a particular angle, is proportional to the cross-section for that angle. And we've already shown that the cross-section for that angle is proportional to 1 over the kinetic energy squared. So we know that the cross-section is proportional to 1 over the kinetic energy squared. And what that tells us is that as the kinetic energy increases, so the number that you would detect at any given angle will decrease. And it's that principle that leads to the next experiment. It's basically the same setup as we've had before. We have an alpha source headed to a target. But on this occasion, the target was lead 208. So instead of gold, we're now using lead. And what we're doing is we are fixing the target at 60 degrees. Sorry, we're fixing the detector at 60 degrees. There is the detector, if you like. And we don't change that angle. We are always measuring how many particles are deflected through an angle of 60 degrees. But what we're going to do is to change the energy of the alpha particles. We can do that using some form of accelerator. I've dealt with linear accelerators and cyclotrons in other videos. They are basically just a means of accelerating alpha particles, giving them greater velocity and therefore greater energy. And for each energy of alpha particles, we measure the number of alpha particles that are scattered through 60 degrees. And remember, we said that as the kinetic energy increases, we would expect the number of alpha particles to decrease. And that's exactly what happened. And here's the results that were obtained. If you plot the number of alpha particles at 60 degrees, it was always at 60 degrees, against the energy in MeV, what they found was that the data points all fell on an anticipated curve which looks like a 1 over Ke squared curve, which is exactly what you'd expect. The number falls off as the inverse of Ke squared until they got to the energy 27.5 MeV. Once they got to that energy, something rather odd happened. Instead of the curve continuing as you would have expected like that, it actually fell off dramatically like that. As the energy increased, so the number of particles deflected through 60 degrees fell off rapidly. And the conclusion was that when you get to 27.5 MeV, the alpha particle has got enough energy to penetrate the nucleus. Beforehand, it was getting stopped before it got to the nucleus by the repulsive Coulomb force. But when the energy is sufficiently great, the Coulomb force can't stop the alpha particle before it actually hits the nucleus and goes inside. And once it gets inside, it is subject to the strong nuclear force, which is an attractive force. Consequently, the alpha particles are trapped. They can't get out. They can't therefore deflect. They are held. And so the number of particles available to be deflected is very, very much smaller. So what we can say is that when the energy is 27.5, that's the point at which the alpha particle is just hitting the nucleus. And consequently R, which we always called the closest approach, now is the true radius of the nucleus. So let me just remind you what R was. It was Q1 Q2 divided by 4 pi epsilon naught times the kinetic energy. And we said that you would simply calculate that by putting in the values of the number of protons in the alpha particle, the number of protons in the nucleus, divided by the energy, multiplied by that constant that we sorted out before. Well, the constant we said was 1.44 times 10 to the minus 15. Now all we've got to do is to put in the values here. Well, the value of Q1 is the number of protons in the alpha particle, that's 2. Q2 is the number of protons in the lead nucleus, remember we're using lead, well that's 82. And divide that by the kinetic energy at the point at which the alpha particle just reaches the nucleus, and that is 27.5. And if you calculate that, you find that R, which is now a good measure of the radius of the nucleus, is 8.59 times 10 to the minus 15 meters. So now we've got a good indication of lead, which is a big atom. 82 protons in lead. There aren't many naturally occurring elements above that. Is about 8.59 times 10 to the minus 15 meters. Very, very small nucleus. And that is about as far as you can go with alpha particle scattering in order to determine the radius of a nucleus. What gives you much more information, not only about the nuclear radius but also about the nuclear structure, is electron scattering. Now the point about an electron is that its mass is very, very much less than the mass of a proton or the mass of an alpha particle. The mass of an electron is very approximately 1/2000th of the mass of a proton. And since an alpha particle consists of 2 protons plus 2 neutrons, and a neutron and a proton, their mass are broadly comparable, that means that the mass of an electron is very approximately 1/8000th of the mass of an alpha particle. So if you want the kinetic energy of the electron to be broadly comparable to the kinetic energy of the alpha particle, remember that kinetic energy is a half mv squared. If in this term m has gone down by a value of 8000, as it would with an electron compared with an alpha particle, that means that if you want the same kinetic energy, v squared has got to increase by a factor of 8000, which means that v has got to increase by a factor of approximately 90. So your electrons need to be going 90 times faster than the alpha particles were if you are going to have electrons with broadly the same energy. We also need to remember, of course, that electrons are negatively charged, and therefore as they approach a positively charged nucleus, the Coulomb force will be an attractive force, but you will still get reflection. It's just that, for example, if this is the nucleus and here comes the alpha particle, if that's an alpha particle, it will deflect that way. If it's an electron, it will deflect in an attracted way. It will deflect that way. You still get deflection, it's just in a different direction. Well, before we proceed, let's just ask the question, why do we have to do all this scattering malarkey? Why don't we just look at a nucleus under a microscope? Well, we've just established that the radius of a nucleus is of the order of 10 to the minus 15 meters. What is the wavelength of light? Well, the wavelength of light is approximately, say, 3 times 10 to the minus 7 meters. Which means that one wavelength of light is 100 million times larger than the radius of the nucleus we're looking at. So if you send a light beam trying to interact with a nucleus, the light beam will simply sail past it without even realizing that it's there. If you want to look at a nucleus, you're going to need a beam that has a wavelength which is of the same order as the size of the nucleus. And that means you're going to need a wavelength not of 3 times 10 to the minus 7 meters, but something of the order of 10 to the minus 15 meters to be comparable with the size of the nucleus. The Stanford Linear Accelerator can produce an electron beam of 6 GeV. How then does that help? Well, let's just convert the energy into joules. 6 GeV will be 6 times 10 to the 9 eV. And then to convert that to joules, we need to multiply by 1.6 times 10 to the minus 19. And that gives you the energy of that electron beam in joules, and that reduces to 9.6 times 10 to the minus 10 joules. And that is equal to the energy, and energy is equal to half mv squared. So if we equate the two, we say that the energy, 9.6 times 10 to the minus 10 joules, is equal to a half mv squared, which is a half times the mass of an electron, which is 9 times 10 to the minus 31, times v squared. And that gives us an opportunity to measure v squared. V squared turns out to be 21.33 times 10 to the 20, which means that v is the square root of that term, which is approximately 4.6 times 10 to the 10 meters per second, which is greater than the speed of light. So that's not possible. And what that tells you, therefore, is that when you've got electrons with that kind of energy, they become what's called relativistic. They cannot exceed the speed of light because special relativity says you can't. So what happens is they get very, very close to the speed of light, but their mass is increased relativistically, and consequently you can never force them to more than the speed of light. So we've got to take another approach. This one's not going to work because it gives us entirely the wrong values. Another way to look at this is to use Einstein's own formula, E equals mc squared. And this is a hand-waving argument. It's not really the proper way of looking at it, but it gives us the right answer. Says that you can regard a mass term as equal to E over c squared. Now the momentum of a particle is mass times velocity. So that's going to equal the mass term, which is E over c squared, we just derived that here, times the velocity v. But I just told you that when you've got electrons at this kind of energy, the velocity is c or thereabouts. So you can replace that term by c, and then one of these c's cancels out, and that just becomes E over c. So now you've got the momentum of the electron with this kind of energy having a value of E over c. Now we have to go to the de Broglie formula, which I've covered in a previous video, which says that the wavelength of an electron is equal to Planck's constant divided by its momentum. Well, we just said that the momentum is E over c, so that means that the wavelength will be h divided by E over c, where E is rather the kinetic energy. So let's just calculate that out. H, Planck's constant, is 6.63 times 10 to the minus 34. The speed of light, c, is 3 times 10 to the 8th meters per second. And that's divided by the energy, which we calculated up here, 9.6 times 10 to the minus 10 joules. And if you calculate that, you will find that lambda, the wavelength of the electron beam with the energy 6 GeV, is 2.1 times 10 to the minus 16 meters. And that energy is comparable, that wavelength is comparable to the radius of the nucleus. So that is capable of probing the nucleus because it will see the nucleus. It's of the same order of size, whereas light would simply go sailing past without even noticing it. Now I just want to make a slight diversion to remind you of the principle of single slit diffraction. If you have light coming through a single slit whose width is d, then the light coming through hitting a screen will in fact be diffracted, and the intensity of that diffraction will look something like that. In other words, opposite the slit you get a very bright amount of light. Intensity is measured in this direction here, and until you get to these points here where the intensity will have fallen to 0. And we calculated that the angle theta, for the first dark fringe, as it were, is given by d, which is the width of the slit, times the sine of the angle theta is equal to the wavelength of the light. And that means that you can say that if you want to calculate the thickness of the slit, that is equal to the wavelength divided by the sine of the angle. Now that is for a slit. If you have a circular aperture, then you have to modify that just slightly by saying that d is 1.22 times lambda divided by sine theta. It simply reflects the fact that this is no longer a slit, this is a circular aperture. And if we're now going to consider, and this is the reason I'm doing this, the idea that the nucleus itself is, as it were, the circular aperture that the electron beam is going to diffract through, then you could say that d is the diameter of the nuclear surface or the nuclear area that the electron is aiming towards. In other words, here is the nucleus, D, and that it behaves like, as it were, the circular aperture. And D is the diameter of that aperture. So the radius is going to be half that. So the radius would be 0.61 times lambda over sine of the angle. Okay, so that's the geometry. Now let's look at some results. And I've drawn out very roughly the results of electron scattering, where the electrons have an energy of 330 MeV, off of a target which is tin, 124 tin, and you're measuring the cross-section and plotting it on a log scale against the angle of scattering. And you get a shape that looks like this. And you'll notice that the first minima occurs at 45 degrees. Now you might wonder why the minimum is not 0, as it would be if you're talking about light. And the reason for that is that the circular aperture isn't perfectly circular. It's got fuzzy edges. And the fuzzy edges are what creates this, the fact that there is still some light, as it were, or in this case electrons are still getting through at the minima. But there's a very clear minimum. The first one is at 45 degrees. So if we regard this electron scattering as the effectively electron diffraction through the nucleus, regarding the nucleus as the circular aperture, then we've got a formula here which will enable us to calculate the radius, provided we know the wavelength, because we know the angle of the first minimum, it's 45 degrees. So we need, first of all, the wavelength of the electron beam. Well, we said that the wavelength, we calculated before, is Planck's constant times the speed of light divided by the energy of the electron beam. Well, Planck's constant, 6.63 times 10 to the minus 34. Speed of light, 3 times 10 to the 8th, divided by the energy, which you'll remember was 330 MeV. So we have to multiply by 10 to the 6 to get it into EV, and then by 1.6 times 10 to the minus 19 to get it into joules. And if you do all of that, you should find that lambda, the wavelength of the electron beam, is 3.7 times 10 to the minus 15 meters. So it's of the right order. It's small enough to interact with the nucleus. And now if you substitute that lambda in this formula here, you'll get that R is equal to 0.61 times lambda, which is 3.7 times 10 to the minus 15, we just calculated that, divided by the sine of 45 degrees, because that was where you got the first minimum, and the sine of 45 degrees is 0.707, and that will give you a radius of 3.19 times 10 to the minus 15 meters. So we're getting more accurate, but we're still getting confirmation that the radius of a nucleus, or in this case the radius of a tin nucleus, is of the order of 10 to the minus 15 meters. Now the point about electron scattering is this, that if you take low energy electrons, then they broadly behave in the same way that alpha particles, low energy alpha particles, behave. That is to say, they never get close to the nucleus, they are simply deflected away from it. And so the Rutherford scattering formula works perfectly fine. For high energy electrons, as we've seen, they become relativistic. They are so energetic that they hit the nucleus and cause the nucleus to recoil. They even have what's called a magnetic moment impact, and so there is a difference in their behaviour from that of the theoretical Rutherford scattering, and when you take that into account you get what's called the Mott cross-section, and that's a refined version of the Rutherford cross-section. Now in the 1950s, a man by the name of Hofstadter did a number of experiments with electron scattering. First, he calculated what the Rutherford cross-sections ought to be. He's plotting cross-section against angle of scattering, the good old-fashioned way. The predicted Rutherford scattering was something like that. The adjusted Mott cross-sections look like something like that. But when he actually did electron scattering, he found that the actual data looked like something like that. And what he was getting evidence of here was something of the nucleus structure. These two terms simply assume Coulomb scattering. But once you get inside the nucleus, you're learning something about the nucleus. And the reason that electrons are so useful is that electrons do not have any impact from the strong nuclear force. Strong nuclear force only applies to baryons, to hadrons. It doesn't apply to leptons. The electrons do not detect and are not influenced in any way by the strong nuclear force. So when an electron gets inside a nucleus, it isn't being held by that force. So you can learn something about the structure of the nucleus by using those high energy electrons. And what was found was that the nucleus is not a, as it were, perfect spherical ball, rather like the billiard ball of old. It is spherical in shape, but with fuzzy edges. In other words, the edge, instead of being kind of a cliff edge, it just slightly tapers off. And this is, as it were, the radius of the nucleus. It was also found that the density of the nucleus is pretty constant throughout. From the scattering techniques over a wide range of elements, it was found that there's a simple formula that enables you to calculate the radius of any given element, and that radius is equal to R0 times a to the 1/3, where a is the nucleon number of the element, that is the total number of protons and neutrons in the element, and R0 is, well, it has varying values. You'll see it sometimes 1.1, anything from 1.1 to 1.3 times 10 to the minus 15 meters. So let's just compare how that formula compares with what we calculated earlier in this video. First of all, for gold, the nuclear radius for gold would be R0 times a to the 3rd, which is, let's use the 1.3 value, times 10 to the minus 15, times a to the 3rd. Well, for gold, a is 197, and a cube root of 197 is 5.818. A to the 3rd is the cube root, and that gives us 7.56 times 10 to the minus 15 meters. But earlier in this video, we said that the closest approach, which we said was not necessarily the radius, we calculated at 4.6 times 10 to the 14 meters. So you can see that the closest approach was a good deal further off than the actual radius of the nucleus. We actually stopped well short of the nucleus itself. Let's also consider the radius of lead. That will be again R0 times a to the 1/3, which will be R0. We'll use 1.3 times 10 to the minus 15 again. This time lead has the value of neutrons plus protons is 208. The cube root of 208 is 5.925, and if you multiply that, you get 7.703 times 10 to the minus 15 meters, whereas when we did the experiment earlier using alpha particles, we got 8.59 times 10 to the minus 15. That was from alpha particle scattering. So we weren't too far off. You remember we said that was when the alpha particles were just beginning to penetrate the nucleus. So that was a pretty good estimate. But anyway, we've established that the radius of a nucleus is pretty clearly of the order of between 10 to the minus 15 and 10 to the minus 14 meters. Finally, I just want to consider the density of a nucleus. Now, density is, of course, typically given by rho is equal to mass divided by volume. That's the definition of density. The mass of any given nucleus will be the number of nucleons in that nucleus, that's the number of protons plus the number of neutrons, multiplied by what's called the atomic mass unit, which is a kind of an averaged value for a proton or a neutron, divided by the volume of that nucleus, which is of course going to be 4/3 pi r cubed, where r is the radius of the nucleus. And we've just said that the radius of the nucleus is equal to r0, which is a constant, times a to the 1/3, which means that an r cubed term would be equal to r0 cubed times a, because a to the 1/3 cubed is a. And so we can say that rho is equal to am divided by 4/3 pi, and then instead of r cubed, we're going to use this term here, r0 cubed times a. The a's cancel, and if you simplify that, you simply get 3m divided by 4 pi r0 cubed, where r0, remember, is the constant. And you'll see that all of that is a constant. We've got m, which is the value of the atomic mass unit, and we've got r0, which itself is a constant. So that tells us that the density of the nucleus is independent of the number of protons or neutrons. The nuclear density is the same for all atoms or all nuclei. And what is that value? Well, let's just work it out. That will be rho will equal 3 times the value of the atomic mass unit, which is 1.66 times 10 to the minus 27, divided by 4 times pi times r0, which again we'll use 1.3 times 10 to the minus 15, cubed. When you work that out, you'll find that that equals 1.8 times 10 to the 17 kilograms per meter cubed. 10 to the 17 is a massive number. To give you some idea, a teaspoonful of a nucleus, if it was just nuclei, no atoms, just pure nuclei, a teaspoon of pure nuclear material would weigh 500 million tons. So be glad you don't have to spoon nuclei into your coffee.